Okay guys, today we're going to talk about accumulation and population density. This is an application of definite integrals that's on the AB portion of the exam. Before we get too in-depth into accumulation and population density, I want to review with you guys area under a curve. If we think that we have a graph here and the velocity, let's say I'm traveling at constant velocity, and that velocity, this is a VT to a T graph. That velocity is, let's say I'm traveling 60 miles per hour. All right, and let's say I travel for 10 hours. All right, now here's a question for you. How far do I travel, or how much distance do I travel? 600 miles. Good. How did we get that 600 miles? We did 60 times 10, right? This is 10 hours, and this is 60 miles per hour. And if we think about the units, 60 miles per hour times 10 hours, the units actually cancel out, and we actually get 600 miles. How is that represented on this curve? Right, that's the area, okay, underneath this curve, right? The area underneath this curve is the area of this rectangle, which is 60 miles per hour times 10 hours. All right, what if I were not going a constant velocity though? What if my velocity increased with time? So now here's my velocity curve, and let's say my velocity, it's linear. Let's say it's linear though, but it increases with time. So let's say I'll travel again for 10 seconds or 10 hours. And my velocity now is a function, and we'll call Vt equal to, let's say, 6t. Okay, so my velocity changes. At time 2, my velocity at this point will be 12, right? At time 4, my velocity at this point will be 24. At time 6, my velocity at this point will be 36. At time 8, my velocity at this point will be 48, and at time 10, my velocity will be 60. But my velocity won't be always 60 miles per hour. This is miles per hour. All right, it changes with time. All right, now if I asked, how far did I travel? How will I do this problem? Well, it's still the area of the curve, and this area is pretty easy to find because it's a triangle. But, let's pretend like, this was bumpy and such. If this had been kind of a bumpy velocity, the way I would have done it is estimate the area under the curve. Okay, do you remember this? What I would say is, okay, let me do a right hand Riemann sum. So if I come up and go to the right, okay, let's see, go to the right and come over, come up on the right number and go over, come up on the right number and go over, and come up on the right number and go over. And I got the area of each of these rectangles, okay? This area right here, so this area right here would be my approximate distance after 2 seconds, right? And this area right here would be my approximate distance after another 2 seconds. And the next area would be my approximate distance, right, after the next 2 seconds. Oops, the next hour, right? The next hour. All right. So the way I would do this is I would get the area underneath each of these curves and add them together. So this would be 12 times 2 plus 24 times 2, right? That's the area of this rectangle. Here's the area of that rectangle, plus 36 times 2 plus, and so on. And if I add all those together, I've done this before I came, I think I got 360. And you can check me on that. It's somewhere close. The area I got here was 600, so really I should have gotten 300. 300 was the exact area. But remember, this is an approximate. Now what does this area under the curve represent? It's the approximate distance, okay, that I traveled. The area under the curve is the approximate distance that I travel. And so that would be 360 miles if my velocity curve was 6t. Well, what if I wanted the exact area under the curve? Well, the exact area under the curve would be taking what I had from these boxes, okay? So what I did with these boxes is I said, okay, first it's VT times delta t, then it was another VT times delta t. This is T1, so to speak. This is T2, plus another VT times delta t. And each of these was one of these rectangles, okay? And I said, you know what, I'm going to add them all together. So I'm going to get the sum of all these VT delta t's, okay? And I want to get the exact area under the curve. So to get the exact distance or the exact area in the curve, what we said was this delta t would get smaller and smaller and smaller. And as it goes to infinity, what would happen is I would get the exact area under the curve. And that was what a definite integral was. It was the integral of Vt dt, okay, from T1 to T2, and that gave me the distance or the area under the curve. Now what's important to note here is basically we're going to do the same thing in all of our accumulation and population problems. It's just that now we won't be talking about miles per hour anymore, okay? We'll be talking about population, like people per mile or people per square area, okay? And so because of that, we just need to look at units and make sure our units work out. So let's think about these units here. If I have, let me scroll down a little bit. If I have v times t, okay, so what's the unit for velocity here? That's miles per hour. And I multiplied by dt. dt has its own units, that's hours. Does it give me distance? Yes, it does, okay? So when we talk about population, if we have people per mile, like that would be a population density. If I want to get the number of people, then what would I have to multiply by? Miles. What if I had people per square mile? So this would be miles squared, people per square mile. If they gave me this as a population density, what would I need to multiply that out to get number of people? I would have to multiply it by square miles, right? Or area, okay? So we're going to have to pay more attention to our units than we did in the past. All right, let's dig in. We're looking at accumulation and population density. In your notes, the first problem says a city located along a straight highway has a population density like this function, px equals 1500 times 4 minus x, where x is the distance from the town squared measured in miles. And then where x is between -4 and 4, and p is measured in people per mile. The town extends for 4 miles on either side of the town square. Find the population of the city. Okay, so the first thing we need to understand is this function here, okay? So if I graph this function, what would it look like? This is going to be the distance. So this measured in miles here. This is distance from the town square. Let me call it 0. This will be the town square. Okay, but if I distribute this 1500, right, this would be 6000 minus 1500x. Okay, so this is what my p function is equal to with respect to x. All right, so this is my p function. If I graph my p function with respect to x, you can see it's a linear function with the negative slope, and 6000 here would be my y-intercept. So if I graph this graph, it would look 6000 here, and it would be negative. Okay, so this is my population density. As I go further away from the town square, right, my population density decreases. And that kind of makes sense in most cities, right? Your population density might be really, really crowded when you're close to town, but as you get further and further away from town, the population, scatters, except for when you get to Cyprus, okay? So if I think about what's going on here, the population density is going to be really high right when I'm at the town square, and then lower as I go over to the right. And it says the find the population of the city. So if this is the population density, let's look at the units for it. It's measured in, let's see, people per mile. So my population density is measured, this is measured in people per mile, okay? And I want to find the population of the city. That's going to be, I want to get that to be equal to number, I want to get that to be equal to number of people. So what am I going to have to multiply it by? By mile, right? All right. So let's think about it. What is a mile? So if this is the population density right here, okay, what I would multiply it by is my delta x, right? And this would be the population, okay, in this region right here. And what if I wanted the next delta x? Wouldn't this be the population right here? This second box be the population for this next delta x? And the next delta x, wouldn't this be the approximate population? Well, so the population is going to be the area under the curve. So what I want to do is take the px, multiply it by each delta x, and sum that all up, okay, as delta x goes to 0, or as n goes to infinity, right? And so what that means is this is the integral, okay, from 0 to, how many miles am I coming out to here? 0 to 4, all right, of px dx. Okay, so this is going to be 0 to 4. The p is 1500, 4 minus x, and the dx is just dx. Okay, now you might be asking, why didn't I put negative 4 here? Because it says we want the total population from negative 4 to 4. All right, let's think about this. If I put negative 4 here, okay, this graph here goes like this. But what is the population density looking like over here? It actually is going to move down, right? Okay, so the population density here would look like this, but then it should decrease as we go away from the town square, right? This thing should decrease. So if I actually get the area under the curve from negative 4 to 4, what would I really be getting? I'd really be getting this large triangle, not the real density that I want. The real density I want is kind of like a triangle with, you know, a negative slope here, or a positive slope here, and a negative slope here, right? I want this triangle, right? Assuming my negative 4 is somewhere over here, all right? I don't want this other triangle caused by this blue line all the way over here. So what I want to do, the best thing to do is actually take this integral and multiply it by 2. So another way to do this problem would be to get a new px on this side, right? This px over here would be the negative slope, so it would be negative the positive slope. So this would be 1500x plus 6000. And so this would be the integral of this px, this green px, which is a different function. I'll call it p2x times delta x from negative 4 to 0 plus 0 to 4 of your original px dx. But that's a lot of work because you have to change the function here to make sure you have this positive slope function. It's a lot easier just to multiply the right side by 2. Let's go ahead and multiply this right side by 2. What I would get is, let me go ahead and pull out the 1500. So out here I'll get 3000. So my answer will be 3000 times the integral of 4 is 4x. The integral of negative x is negative x squared over 2. There's my win bar. I'll take this from 0 to 4. Then what I have is 3000 times, first I plug in the 4. That'll be 16 minus 4 times 2. 4 squared is 16, so that'll be 8. And then plug in the 0. That'll be 0 minus 0. Then I slap a minus sign in between. And don't forget that this 3000 will be multiplied by this whole thing. So what I get is 3000 times 8, which would be 24 100,000 people. Okay, so if you look at this problem right here on your notes, this is a city that's more like a real city. A city can be approximated by a circle. The radius of this circle goes 8 miles. So this 8 is kind of like your 4 miles before. Okay, it's going to go all the way to 8 miles. Moving away from the center of the city along the radius, the population density can be approximated by this function here, where PR is measured in people per square mile and R is measured in miles. All right. So what we're going to do is we're going to draw the same graph. Okay, and we're going to say this is the center right here. This is the center of the city. Okay, and let's do the population density again. This is my population density, and this is miles. So we're going to go X miles away from the city. All right, the units for population density is going to be people per square mile. So this is people per miles square. All right, and this picture, and you don't have to draw it right, but it helps you if you draw it right. All right, we know this is an e to the negative x picture, so it'll look something like, see, e to the x looks like this, right? So e, like this. Okay, you don't have to draw it exactly right. All right, so what we're going to do is we're going to say, you know what if I wanted the population? Well, the population would be people times square miles, right? People times square miles. Okay, so how do I find square miles here? I'm going to move from here to a delta x, right? Or a delta r here. So delta r, okay? And if I wanted the population in this area right here, okay, in this first circle right here, okay, and this circle goes out a delta r, okay, how would I find the area of this? Well, think about it. It'll be people per square mile, and I want to multiply that by miles squared, right, in order to get the number of people. So I need to multiply by some sort of area. What kind of area would I multiply by? It's got to be something that r gets bigger and bigger and bigger and bigger. Okay, so this needs to be, has to have a delta r in it, if that makes any sense. Okay, so what I'm going to do is think about it. I'm going to move out another delta r, like this would be another delta r. Then I would move out another delta r, okay, and this distance right here would be my delta r. So I want you to just look at this ring right here that's already been labeled delta r. That's some random delta r, all right? And how do I get the area of that right there? Because if I could get the area of that, that's what I need to put in right here in this box, all right? Let's cut this thing. Remember, delta r is actually really, really small. Okay, it's big here, you could see it, but we really should have drawn it so skinny that it was like a string, because delta r is going to go to 0 in our integral, right? So let's take this delta r and let's cut it right here because it's like a string. If I cut this delta r here, do you see that what would happen is it would just be like a skinny string, okay? And what would be the area of this string? The area of the string would be delta r, okay, going this way. So I guess this is really r, okay, delta r going this way. What would be the height of this string, or the length of this string? What would be the length of this string if I cut it? It'd be 2 pi r, right? So the area of one of these red boxes, each one of these red boxes, so I'll make another box, and then another box, and another box, okay? Each of these areas is actually 2 pi r times delta r, right? And what I want to do is I want to take this area, okay, and multiply it by people per square mile, and that will give me number of people. So the number of people in this first box is going to be this PR, okay, it'll be this PR, population density, okay, times the area of this box. So it'll be 2 pi r delta r. And then the next box here Okay, I'll do it in green. The next area here, okay, that area is going to be 2 pi r delta r. Okay, I guess the next r. So this first one would be plugging in the first r, and then the second one would be plugging in the second r. Okay, and this would also be pr. Okay, then I add those together, right? And then I would add the next one together, the number of population in this area, and then I would add the population in this area. When I add all those populations together, what I end up getting is the integral of PR 2 pi r delta r. Okay? And as I get this, this will be integrated. Okay? This is the same thing as the integral of PR 2 pi r dr. Okay? And that'll go from what's my smallest r to my largest r. My smallest r is going to be 0, and what's my largest r? It'll be 8. Okay? And each one will take care of like one of these rings. Okay? So I don't need to multiply this by 2 because I'm already taking care of every single side from the center when I do this equation. All right? Now notice this PR here is actually just a function of the population density. All right, so you just multiply it by some function. The PR needs to be inside of the integral because the R changes. There's an R here. The R changes with the population, right? If it were constant, you could pull it out, but since it's not constant, you have to leave it in here. This R here also changes as R gets bigger and bigger, so this R needs to be integrated. And of course, dr is in the inside of the integral. So if I were to solve this, okay, this answer would be the integral from 0 to 8. PR is 2,000. So I'm going to pull the 2,000 out if that's okay with you. 2,000 times e negative 0.15 r times 2 pi times r dr. What else could I pull out? I could also pull this 2 pi out, right? So this is 2 pi times 2,000 on the outside here. This would be 4,000 pi 0 to 8 e to negative 0.15 r dr. Okay, I don't think I could do this by hand. I don't think it's going to, the x's are going to cancel out. So what I need to do is get my calculator out. This will be a math 9 from 0 to 8 e to the negative 0.15 x times x, and this will be an x. I know I'm using x's instead of r's, but my calculator doesn't know that I'm using x's instead of r's. Shh, don't tell it. And so this is going to be the integral. Don't forget to multiply by 4,000 and multiply by pi. And so this is the number of people. This is a population. So my answer is 188,424.480 people. And I know that I wouldn't have a 0.480 person unless that person was super short. So the answer, well, I would leave the answer like this just because it's a BC test and you always round to 3 decimal places unless they tell you otherwise. All right. Write an expression to represent the number of people in the shaded ring. All right, let's just talk about that answer. The shaded ring, one of these shaded rings was, remember, it's the area of this rectangle times PR, because one of these shaded rings is one of these rectangles, right? So let me just answer letter A. Letter A here is going to be P times R, the population density, times the area of one of these rectangles. So 2 pi R delta R. Okay, so make sure you know how to do that for letter A. And then, let me see, this would be number of people in one ring. find the population of the city. So this answer goes with the population. Let's do another example. Water is pumped out of a holding tank at a rate of 4 minus 4e to negative 0.12 t liters per minute, where t is in minutes since the pump is started. If the holding tank contains 300 liters of water when the pump is started, how much water does the tank hold 20 minutes later? All right, so this is a similar problem with population density, but since it's time, time is a lot easier for us to understand. And the one thing they do add in here is we do have kind of an initial population or initial amount of water. So that's 300. All right. So how would you do this problem? There's several ways to do it, but let me go ahead and draw a picture to make sure we understand what's happening. I've got this holding tank, right? And inside this holding tank, I already have 300 liters of water, okay, at time equals 0. All right. And then water is being pumped out of it. So going out of this tank, okay, is a water being pumped out at a rate. Like this is liters, but this one is going to be liters per minute. So I'll just call that dV dt, all right? And that's 4 minus 4e to the negative 0.12 t liters per minute, okay? And so what do I have to do if I want to get liters, right? I want to get the amount of water 20 minutes later, all right? So there's several ways to do it, but one way to do it is to say, okay, well, in 20 minutes, how much water is going to be pumped out of the tank? In 20 minutes, I will have 0 to 24 minus 4e to the negative 0.12 t. That's how much water I'm going to lose from the tank in 20 minutes. If I started out with 300 liters in the tank, right, then I subtract this amount, then I should get the answer. Let's go ahead and do this in the calculator. I'll do a math 9 from 0 to 20. 4 minus 4e negative 0.12 t, and I'm going to put x's instead of t's, but my calculator doesn't know. And I need to subtract that number from 300. And that is the number of liters I have in my tank after 20 minutes. Let's look at number 4 together. This says the greater Seattle can be approximated by a semicircle of radius 5 miles with its center on the shoreline of Puget Sound. So cities like Seattle, they don't have like a whole circle around them because, you know, they've got water on this side. So their population density increases, okay, as they get further and further away from the city center, but it only increases in semicircles rather than in full circles, right? And so your R is going to be increasing this way. Here they call it X instead of R. And what this says is that you're given a population density with respect to X. So the population density changes as you move further and further out. And this population density is measured in people per square mile. So if you want to find the population of the city, you're going to need to multiply this population density times square mile, right? Times square mile, okay, in order to get the number of people, all right, if we're just looking at units. All right, so how do I get square mile here? Well, the area is going to be the area of a semicircle instead of the area of a rectangle, okay? But we've done areas of semicircles. If we think about this distance here as being delta x, what's this area right here? Okay, well, the way you do it is, remember, delta x is like a super, super skinny semicircle. So you can actually straighten it out, okay, to get that area. And the width of this rectangle is going to be delta x, all right? And then right next to it, you know, I have another rectangle, right? And the width of that will be your next delta x, okay, and so on, right? We have multiple rectangles, and the widths will be delta x. Well, what's the area of one of these rectangles. Well, the width is delta x. The height is going to be the perimeter of the circle divided by 2. So this will be 2 pi r divided by 2, which is just pi r. So the area of this red rectangle will be pi r times delta x. What's the area of the green rectangle going to be? That's going to be pi r delta x. What's the area of the blue rectangle going to be? That'll be another pi r delta x. And if I wanted the population in the red rectangle, what would I multiply the area by? If this represents the area pi r delta x, then I multiply it by p of x. So if I wanted just for the red rectangle, so let me do it in red. If I wanted the population for the red rectangle population, that's going to be p times x, the population density, times the square miles, which will be the area, pi r delta x. But I don't want just the red population, right? I want all of them. So what I'm going to have to do is add all of these px pi. This is p of x, not p times x. So p of x times pi r delta x. Add them all together and take the limit as delta x goes to 0. All right, if I add them all up and I take the limit as delta x goes to 0, what happens is this delta x gets smaller and smaller and smaller. I'll get the exact population. So this will give me the integral of px pi r, oops, that's not an r, pi x dx. And that will go from 0 to, what's my biggest x? 5. And you can do the rest on your own. Good luck on your homework.